The amazing Cassini spacecraft and its sibling lander Huygens have now concluded their scientific studies, bringing back years of data to be combed through by scientists, plotting their next journey to Saturn's space. Now it's time for other planets and other spacecraft to shine. Juno piercing the cloak of Jupiter, and her distant relative New Horizons at the edge of the solar system. After 20 years, the Cassini project finally comes to an end in dramatic style. But with one door closing, another opens. Now the enviable task of having to unravel the data Saturn has just laid bare begins. And they have literally just scratched the surface.
I think Cassini has left us with humankind's presence at another planet for 13 years, seeing things that we had never imagined seeing, and at the same time sharing that with the entire world and opening up vistas for the next sets of missions.
One of the issues facing scientists when looking at exploring the new frontier is leaving it in a better state than they found it. So eliminating the problems of space junk or the introduction of alien microbes is paramount in their decision-making.
But it also helps us satisfy a planetary protection requirement. We're protecting the tiny moon Enceladus as well as Titan. Both of those have global oceans underneath their icy crusts, and just in case there might be life in those oceans, we don't want Cassini to crash into one of those moons once we're out of fuel.
While the main focus of the Cassini mission was to delve into the mysteries of Saturn and its rings, the moons of Saturn proved most science-worthy. And Saturn has many moons. In fact, 62 with confirmed orbits. Several are only 50 kilometers in diameter, the largest being Titan, which is bigger than Mercury. The Huygens module that traveled aboard Cassini also became the first probe to land on a moon other than our own and transmit data back to Earth.
The temperature at the surface of Titan is about minus 180 degrees, so it's very cold. The landscapes of Titan look a lot like those we have on Earth. We have rivers, lakes, seas, almost oceans of methane. It rains methane or a mix of ethane and methane, so there are lots of meteorological phenomena or geophysical phenomena on Titan that makes you think of what happens on Earth. But the ingredients are quite different.
But it is Saturn's sixth largest moon that excited many scientists, as it is virtually covered by clean ice and ejected plumes of water into space.
My favorite moon is Enceladus, and the reason I'm partial to Enceladus is it's the moon that my team discovered a water vapor plume at. But not only is there liquid water underneath the surface, but there's organic material, there's a heat source. You know, when people get excited about the potential for life elsewhere in the solar system, there are four things that you need. You need a heat source, You need liquid water, you need organic material, and you need those three things to be stable over some period of time so that life could potentially form. At Enceladus, we've got three. We're not sure about the stability over time yet. And so based on the Cassini observations we made back in 2005, we've had lots and lots more flybys of Enceladus. We now understand it much better. We understand what organic material is there. I mean, one of the instruments, the ion neutral mass spectrometer, in a very close flyby through the plume, found some ammonia in the plume.
First of all, we see plumes. Then we start finding out from the gravity measurements and the imaging that there's an ocean and that it's global. And then there was some measurements by the cosmic dust analyzer that suggested there was hot water being circulated through the rock, the silicon dioxide nanoparticles. This is just the final step that shows that there's molecular hydrogen being produced by these same hydrothermal processes, and that molecular hydrogen has the chemical energy to support microbial systems in the interior ocean.
It's really the longevity of the Cassini mission that's allowed us to put together the pieces of the puzzle to really understand a moon like Enceladus. And even this late in the mission, we continue to look at our data to better understand this ocean world.
Collating data is one thing, but interpreting and providing vision for future missions is another. This is an area for which the Cassini project came up trumps, because it not only brought together three agencies, it provided the ground for future scientists to develop skills that will provide the basis for new projects.
The number of PhDs we've put through the system that are going to be the educators of the next generations. We've put out 3,000 plus peer-reviewed papers, hundreds of PhDs, thousands of peer-reviewed papers. The legacy, the scientific legacy is huge. The engineering legacy, of using every ounce of engineering capability to exploit a system, I think is again, we will be built upon. And I can't ignore the international cooperation. I mean, we had 19 nations contributing hardware to this mission. We've got over 26 nations now contributing scientifically. And despite whatever else is going on, this really has been an amazing collaboration with across the world.
The mighty Jupiter is the current target under the microscope with the Juno mission in full swing. The story of our solar system is linked to Jupiter, as it is believed that it was the first planet formed. So if we can understand how, we can begin to unravel the origins of our solar system, and thus how the Earth came about. Juno must work in a very harsh environment to tease out the answers from the gas giant.
When you go to a place as hazardous as Jupiter, we put a lot of time through the whole development process in trying to design a spacecraft that will operate in the high radiation fields, the magnetic environment, the spacecraft charging environment, everything that you deal with at Jupiter. And I have to say the spacecraft has been performing admirably.
Jupiter's radiation belts pose one of the biggest problems faced by Juno scientists. They exist within the enormous magnetic field that surrounds Jupiter, with its magnetosphere trapping and accelerating particles. It produces intense belts of radiation similar to Earth's Van Allen belts, but thousands of times stronger.
Juno just flew by Jupiter for the first time with all the science instruments on, and it was spectacular. The spacecraft performed flawlessly, the instruments all worked exactly as planned, and the data is amazing. We're looking deep into Jupiter, we're learning about the secrets that it's holding, but we're also getting a lot of surprises about the aurora, about the atmosphere, how it works. I mean, it's just incredible.
The flybys which followed showed that the massive amounts of energy swirling over Jupiter's polar regions were creating the giant planet's powerful auroras, but not in ways the researchers expected. What puzzled the researchers was the fact that despite the magnitude of these potentials at Jupiter, they are observed only sometimes, and are not the source of the most intense auroras as they are on Earth.
Juno had its camera, Juno Cam, on during the flyby. We got the first pictures of Jupiter's poles, the North and South Pole. They were amazing, a lot of surprises in them. It didn't look like we thought, doesn't look much like Saturn's pole.
Jupiter's poles are covered in these cyclones and anticyclone storms, some of them half the size of the Earth or bigger. And we're puzzled as to how they could be formed and stable in that configuration. And the North Pole doesn't look like the South Pole. And so we're questioning, the scientists are really questioning whether this is a dynamic system and are we seeing just one stage and over the next year we're going to watch it disappear? Or is this a stable configuration and that these storms are circulating around each other?
While the polar activity appears unique to our solar system, the engineers are looking below its shell for answers.
The new science results from Juno really are our first look at close-up at how Jupiter works. And so the first time we're looking inside of Jupiter with into the interior, and what we're seeing is that it doesn't work at all like we had predicted. Almost every model that has the interior motion, how the magnetic field, the gravity field, how the deep atmosphere works, it's all different.
Like most scientific undertakings, they result in more questions being asked than answered.
So Juno's original objectives really were to understand how Jupiter formed, and that would help us understand how planets general form and how the whole solar system was made. What we're finding is that actually we didn't understand giant planet dynamics very well, the whole atmosphere or interior structure.
What we've seen so far is exciting, no question about that. But it's like a puzzle, and we're putting the pieces of the puzzle together, and it's exciting, but we don't have the whole picture yet.
And one of those puzzles is the so-called Great Red Spot. And while its presence in a turbulent gaseous planet is not unusual, the scale is. The red spot covers an area twice as large as Earth.
And we're going to go right over the Great Red Spot. And that's really going to be the first time that we get a close look at that and to see what it's like underneath the top surface layer. I mean, how deep are the roots to that? That's a 300-year-old storm. A lot of scientists believe that the roots must be very deep. Well, when we go over with our microwave radiometer, we're going to see, is it the same as the zones and belts, or is it very different? And nobody really knows.
But it's not just Jupiter's poles that hold the greatest interest for the Juno investigators. They are also intrigued by the weather pattern that is unique to this planet, yet familiar in other ways. Studying the atmospheric dynamics helps understand other planets' atmospheres.
So when we look at Jupiter, we see a lot of structure that looks very similar to the Earth. We can see storms, we see cyclones, we see anticyclones, and these sort of storms and weather systems that we see on Earth are very similar, and they're happening on Jupiter. Fluid mechanics is hopefully the same everywhere in the universe, but Jupiter and Earth are very different. Jupiter is much bigger, it rotates a lot faster, they're made of different material, and Jupiter's much further away from the sun than the Earth is. The quasi-biennial oscillation, or the QBO, on Earth is an equatorial phenomenon in the stratosphere where the winds are changing direction approximately every 2 years. Depending on which phase the QBO is in, eastward or westward, the temperature signal corresponds to that, so it's warmer in the eastward phase and cooler in the westward phase. It's been shown that it can actually be a barrier to transport of aerosols across the equator and has been linked to the frequency and the formation of hurricanes in the Atlantic and the Pacific Ocean. The long-term scales on Earth's climate is something that we're very interested in, and how that applies to other planets' atmospheres is really why we're studying Earth and Jupiter. The quasi-quadrennial oscillation in Jupiter's stratosphere is a temperature signal that we see in the equator, where we see the temperature get warmer and cooler approximately every 4 Earth years. We used a general circulation model where we focused on simulating the effects of small-scale waves produced from convection in Jupiter's equatorial region to simulate the QQO. The waves propagate upwards from the clouds and force the winds in the stratosphere to change direction, going from eastward to westward approximately every 4 years. Our model was able to reproduce the behavior of the QQO, but was also able to reproduce temperatures from the observations, and both of those together give us a lot of confidence that our model is very accurate in what's driving the QQO. The outer planets serve as a laboratory for understanding atmospheric physics under very different conditions that are present on the Earth. Understanding how their atmospheres change and evolve and their climates can give us insight into any planetary atmosphere.
Juno has studied the planet with a suite of tools, revealing much that was previously hidden to the human eye.
We have an infrared instrument on Juno called GIRAM, and it was designed and built and delivered by the Italian Space Agency. And this instrument makes thermal maps of Jupiter. So the images are showing you what's warm, hot, cold on Jupiter. And one of the things you can see right away is the center of some of these hurricane-like storms are cooler than the surrounding area. And sometimes you go over a warm spot. And we went over one that was very small that seems hotter than the surrounding area. And that's very similar to what the Galileo probe went into back in 1995.
The Juno mission is unique because it's the first time that we've ever gone in a polar orbit, which goes from pole to pole, over the North Pole, through periapsis, and under the South Pole. All the other missions we've done and all the observations we made from Earth were made from the equator. And you don't see the poles very well if you're sitting on the equator. Yes, this is the first time we get the first clear, unobstructed view of what the aurora looks like and what the polar phenomena looks like. And at the same time, we're flying through the magnetosphere right above the aurora, so we can sample in situ the charged particles that are precipitating down magnetic field lines, the guys that are exciting the emissions that we see.
Juno, like its sister Cassini, has a use-by date when the craft runs out of maneuvering fuel. This may occur during its 12th orbit at the end of its prime mission. However, NASA may choose to extend the mission if there are sufficient reserves. In that case, the deorbit would occur later, on the 34th orbit, as part of the planetary protection policy of NASA. Its pathfinding mission is leading the way for the one to come, the Europa Clipper, a mission in the design phase to look closely at Europa, the moon with a hidden ocean, and the possible location for life to evolve beyond Earth. The blue haze of Pluto's atmosphere, possibly a hydrocarbon smog, seen from 200,000 kilometers away by NASA's departing New Horizons spacecraft. A few years ago, the dwarf planet Pluto and its 5 known moons were just small dots in the outer reaches of our solar system.
One of the important things you should understand about Pluto is the real scale of it compared to the rest of the solar system. So we've come to the beach to really convey that scale and distance. So if I draw the sun as a 30 centimeter circle, then we have to walk about 35 steps this way in order to draw the Earth in the same type of scale. So we're walking the equivalent of 150 million kilometers, which we call 1 astronomical unit. Normally, Pluto orbits at about 40 astronomical units from the Sun, but it's actually quite an elliptical orbit, so it changes between about 30 and 50 astronomical units. But back to the Earth. So the Sun is over there at 30 centimeters, which means that the Earth should be about here, about 3 millimeters, something like this. If we were to draw Pluto in the same scale, it should be 0.3 millimeters, and it should be 1 kilometer down the beach. So I'm going to draw it. Now obviously I can't draw something that's 0.3 millimeters, so I have to draw Pluto a bit bigger. If this is Pluto, then its largest moon is Charon, which is about half its size. But Pluto has 4 other moons: Styx, Nix, Kerberos and Hydra. So there's a lot going on around the Pluto system. It's not just a cold, dead, icy rock.
The spacecraft spent 16 months sending its data back to Earth, and scientists and non-scientists alike have been enthralled by what it has revealed.
If you go in closer to the surface, you can see this type of really diverse terrain. So you have a very bright region. These are flat plains. We're not entirely sure how they formed yet, but there's a couple of leading theories. There's a huge range of mountains. There's all kinds of different aged surfaces. Some of them have lots of craters. Some of them have very few, which means they're younger. If you look at, in a lot of detail at some of the mountainous regions, you can see that actually they're a few kilometers high, but they're made of water ice. I mean, on Pluto, it's so cold that water ice is the hardest thing. It's more like rock. And so the stuff that forms the softer material is actually nitrogen ice.
Water ice on Earth is close to 0 degrees, but on Pluto, it's minus 230 degrees Celsius. And there's a glacier of nitrogen ice, called Sputnik Planitia, thought to be under 1 million years old. This is young by planetary standards, and no one knows yet how it formed or is renewed.
One of the really fascinating things is some of the surface coloration you can see in these images actually shows that there are these compounds called tholins, which are a combination of elements, but they're related to prebiotic molecules, so they're kind of relevant to prebiotic chemistry. And I think the fact that they have been able to form on planetary surfaces very far out in the solar system at very cold temperatures really has implications for a lot of places. I mean, if you can imagine for star systems outside our own, where the star may be dim and the planets are quite far away, it's interesting to know that there are molecules that could be involved in supplying biotic material to processes that may one day lead to life or be involved in life or something like that. That they're actually forming way out in the solar system where no one really expected.
Pluto is unlike anything seen before. But the 6 gigabytes of New Horizons images and scientific measurements are giving scientists mysteries to unravel for years to come. In the meantime, asleep for the moment, the probe travels deeper into the unknown, soon to awaken at its next destination.